Hello everyone, welcome to join our session. This is AI for all people. It's like data for all people, but kind of similar because most of the most important part of AI is data. So I think AI for data for all people, it has critical um, component is accompanying our data providers to help us to achieve all these insights, to get all these insights from the AI model, using AI models from the dataset. So we organize this session. This is actually an extension session by the ECA machine learning cluster, and we have regular meeting on every third Friday. Sorry, third Friday at uh, 1, I think 12, sorry, 12 p.m. Eastern time. So we are actually focusing on some like concrete achievements, like writing some white papers, and which we already write paper about reviewing all the previous AI research in the Earth system science. And that paper has already published on the computer science, computers and geoscience. And it's the most popular paper right now. So yeah, that's kind of our looking back, looking back what we have achieved. And we found a lot of challenges and also opportunities ahead of us. Um, so what are next? Next is actually because the major problem is AI is not practical. We can see that definitely because all the data products, most of them are just concrete, very fixed, validated, very reliable. But have you seen any data set that is produced by the AI and operationally used by people? I would say I haven't seen any. You know, it's not practical, but we have to figure out why. So we are working on a practical AI white paper right now. So we are asking the community input. So anybody is welcome to join. Even you are not an AI specialist, but you are welcome to join us. Um, we collaborate on the Google Drive, so uh, it's open access to everybody. So no pressure and welcome. Okay, so we are ordered to invite several speakers, our regular uh, attendees of the machine learning cluster, and the first speaker is going to be Amruta Kyle from University of Idaho, and she is going to talk about provenance and to enable the explainable, trustworthy AI in the earth science. Welcome, all yours.
Hello everyone, Amruta Kale again. We have seen rapid deployment of systems using artificial intelligence and machine learning in various critical domains like healthcare, human resource, where decisions taken by AI and machine learning algorithms affect human life. However, existing AI and machine learning algorithms are insufficient to certify how and why the results were obtained, which leads to growing concern that these AI and machine learning algorithms are unfair, opaque, and non intuitive, which is why the topic of trustworthy AI has received a lot of attention in recent years. The term trustworthy AI is used to describe that AI is lawful, ethical, and technically robust to ensure that humans could rely on them. It is based on the idea that AI should reach its full potential based on development, deployment, and use. And one of the feasible steps in developing a trustworthy AI model is through
You have
explainable
not
AI.
considered this knitted t-shirt.
Explainable AI refers to a series of frameworks and techniques used to ensure that the results generated by AI and machine learning models are interpretable and understandable while maintaining high predictive accuracy. The given image is captured from DARPA's Explainable AI program, where it aims to create a series of new explainable AI models while maintaining high predictive accuracy. The first half of the image, as you can see, is the traditional machine learning model, where we have the training data, we apply some machine learning process, the machine learned itself and generates some output. But in most of the cases, the user is unable to understand why the machine generated a certain result or why did even the machine fail? But with the new explainable AI technique, we will have new machine learning techniques, an explainable AI model, along with an explainable interface, which will allow user to understand why did the machine fail or why did machine even uh, generated a particular output. The need for explainability has received a great tension in recent years. We have seen several controversies where the results generated by AI and machine learning models have generated biased or discriminatory results. And here are few of the examples. The risk assessment tool used in US courts have shown to be biased against the black people. It shows that the black people have high risk of being a criminal as compared to the white people. Amazon recruiting tool have shown to be biased against women. Amazon designed a recruiting tool to hire people. For a certain period of time, there were more male candidates who were applying for the position. It turned out that the machine learned itself that male candidates are more preferable as compared to female candidate, leading it to gender bias. A self-driving car killed a woman in Arizona considering it as a plastic bag. It turned out that the automatic car software was unable to identify if the person was jaywalking or was on the crosswalk. In 2016, Microsoft designed a Twitter bot called Tail, which was designed to entertain and engage people. In less than 24 hours, Tail's talk extended to racist and offensive comments, forcing Microsoft to take it offline. After these many discriminatory results or incidents, there have been a lot of research which is going on trustworthy AI and explainable AI to make AI more explainable and transparent. And here are a few of the ongoing research. In 2017, the Defense Advanced Research Project Agency DARPA funded an explainable AI program. In May 2018, European Parliament set the rule for a general data protection regulation to award citizen right to explanation. In 2019, the government of Finland published a final report on Finland's artificial intelligence program in order to position Finland as a leader in application of AI. To encourage public trust and promoting the use of AI in federal government, the White House signed an executive orders on trustworthy AI. We have also seen the great success in academia as well. National Science Foundation and the recent article published by Dr. Janet Wing in CACM has also considered trustworthy AI as an emerging topic and focus on different approach which should be considered when developing or building a trustworthy AI. Before talking more about explainability, let's even understand the basic types of machine learning models and why these machine learning models needs to be explainable or transparent. Typically, there are two types of machine learning model, transparent model and opaque models. Transparent models are interpretable by nature. When you run these models, they generate some form of output which is understandable to humans. But do not generate these modules are not highly accurate, while opaque models are black box in nature. Despite of high predictive accuracy, these models cannot be reviewed. So we can definitely see that there is a contrast or there is a gap. Opaque models are highly accurate, but they are not more interpretable. Sometimes even the developer who is designing these model is unable to understand why did the model behaves in a certain way or why did even the model generated a particular output. While interpretable models or transparent models are interpretable in nature, but these are less accurate. So people have come up with a solution, which is popularly known as post hoc explainability approach. In post hoc explainability approach, you first train the opaque model, then apply a different model to understand what the existing model has learned, so that the user can understand the final outcome with an explainability. But these post hoc explainability approaches are at a very infancy stage, and we believe they lack metadata information, which is why we believe provenance plays a very important role in bringing explainability and transparency in AI and machine learning models. Let me talk more about provenance. Provenance is the origin or source of something. Provenance helps us in understanding how the data was collected so that it can be meaningfully used. Provenance helps us in determining the ownership and rights over an object. Provenance helps us in making judgment about information to determine whether to trust it or not. We believe provenance definitely adds more explainability and transparency in AI and machine learning model. And using provenance will not only provide an explanation, but it will also improve the understandability and explainability of AI and machine learning models. It will help to reduce or identify the biased or discriminatory results which have been generated by these models. To increase transparency in AI-based system, provenance documentation is an efficient way to provide well-grounded information about data, software, hardware, and other components that forms the workflow. We also did some bibliometric analysis to find out how provenance, AI, and machine learning are interrelated to each other. We restricted our search for the past 10 years and we focused our only Scopus dataset. And we found out that from 2018 to 2019, we can definitely see that there is an exponential rise in the number of publications where people are more focusing on provenance, AI, and machine learning together. We can also see the analysis by subject area. There is no doubt that computer science is most dominating field which is doing the research in AI and machine learning. But it is also interesting to see other fields like social science, medicine, agriculture, earth and planetary, which are also taking a greater interest in AI and machine learning models along with provenance together. And here is the correlation of author's keyword. The author's keyword definitely shows the four different clusters, but we can definitely see that provenance and machine learning are highly interrelated to each other. But there has not much research going on. Our objective with this research is provenance has the capability of explanation and it has not received the great attention which it deserves. We believe inclusion of provenance can definitely address the what and why aspects by documenting the entire process. And we will demonstrate this with the help of provenance-enabled platform named GeoViewer. I believe Dr. Sun is definitely going to talk more in detail about GeoViewer, but let me give you the brief idea about GeoViewer. GeoViewer is a web-based application which allows users to compose, create, execute, and build AI workflows all in one place. The core framework of GeoViewer is divided into three basic modules: host, process, and workflows. The host module allows users to connect to different resources based on different resources or virtual computing platforms like Google Earth. The process module allows user to create or write Python program or bash scripts or shell scripts in the same user interface. And the workflow module allows user to create workflows based on the existing process. Our research focused majorly on provenance and documenting provenance. And the best part about GeoViewer is that it is provenance enabled. It tracks the history of each and every process which has been generated in GeoViewer or which has been created in GeoViewer. The Weaver workspace allows user to create workflows from the existing process. And it also shows the real-time status of each process while creating or running the workflow. The red indicates that the process has been failed. The green indicates that the process is running, while the yellow indicates that the green indicates that the process has been run successfully, and the yellow indicates that the process is running. The GeoViewer also provides you the option to download these workflows. It provides two options, one with the process code and workflow, and one with the process code, history, and workflow file. Our objective or our work collaboration with this research is to translate these workflows into a common workflow language. Common workflow language is a standard which is designed to explain or describe workflows. For this, we have created GeoViewer CWL, a Python package which automatically translates these GeoViewer AI workflows into common workflow language scripts. The basic function of GeoViewer CWL package includes GeoViewer generate CWL and generate YAML. The generate CWL function takes input, which is workflow.json, and translates it into workflow.cwl. Along with that, it also takes all the code from the process folder and translates all those files which are available in the process folder into CWL. The generate YAML file has to be given an input and translates or generates an input file to run the workflow.cwl file. Here is the given example of how the translated workflow looks like. There have been several platforms which are used for translation, but most of them lack interoperability in them, and which is why we used CWL. And here are some of the benefits of CWL. CWL includes flexibility, portability, and scalability. And translating GeoWeaver AI workflows into CWL will allow Earth scientists to easily share, exchange, modify, and reuse and build new workflows from them. CWL is well suited for describing large-scale workflows in cluster, and applications written in CWL are highly portable and can be executed in a variety of environments, including local and cloud. CWL supports software components, containers, and container technologies such as Docker and Singularity to enable portability. For our future work, we hope to use more on GeoWeaver, test more use cases on GeoWeaver, and improve the usability of GeoWeaver and GeoWeaver CWL Python package. Thank you.
Okay, so I think we have to presentation.
Just a couple of points. It's always useful to remember that there are marginalized communities that have good reasons not to trust AI. So even if you put trustworthy AI at the center, they should not trust it. So when you expand on scientific. Second of all, it might be useful when you're thinking about metadata to include how many sensitivity tests have been done. So how sensitive the model is to different kinds of feature engineering. For example, I've heard a lot about the GAN approach to some of these models.
Thank you so much for your feedback.
You want to answer? Yeah, I think we have to.
Yeah, but I don't have an answer for that right now, but I will definitely keep it. Take a note and then probably work on it. Thank you so much.
I think the point is but I think the point is people probably have a lot of questions.
About trustworthy AI? Yeah, it is just an idea to build an explainable AI model, and to build an explainable AI model more trustworthy, it is just a concept which has built. But we are focusing more on provenance.
Okay.
Yeah.
I think we will cover some of those concerns in my talk. Because I think a trustworthy AI is kind of like all those problems is done from the randomness in AI. And every time you run the AI, it's actually parallel universal. So we record everything in there. Every time when it runs, we record everything. The provenance, you can see exactly what happened and why it got out. That's we call trustworthy. It's not like the AI itself is trustworthy, but it's actually the whole process. It's like we capture everything. That's the point. Yeah. Thank you. Thank you so much, everyone. I think next. Oops. Yeah, I think the next speaker is. Let me see.
You got it?
Where is the mic's slide? Oh, Mike, do you want to share your screen or?
Yeah, let me pull that up. Hopefully that's displaying for you all.
Yes, we can see that.
Awesome.
Okay.
Awesome. Our next speaker is Mike from Sunny ESF. So he's gonna talk about how to build trust in the AI output. So he'll talk about it from his use case, like using in New York's forest carbon monitoring program. So take it away.
Awesome. Thank you. Yeah. Thanks everyone for being there. I'm sorry that I'm not able to join you all in person, but I am really excited to talk to you all about building trust in AI outputs. And I'm specifically going to talk about the steps that we're taking as part of New York State's forest carbon monitoring program to try and build some of that trust in the results that we are generating in our generated data products. Before I get to that, I'm going to start with a bit of context, including introducing myself. So I am Mike Mahoney, and I'm a PhD student at the State University of New York College of Environmental Science and Forestry, as well as a community fellow here at ESIP, working with the machine learning cluster. And if you want to follow along or find these later, these slides are available from my website. They're at mm218.dev/ESIP2022. And so over the past few years, I've been lucky enough to have this really interesting applied AI machine learning problem. See, New York State in 2019 passed its Climate Leadership and Community Protection Act, which is New York State's net zero carbon bill. It mandates that by 2050, New York State needs to hit net zero emissions statewide, and by the same year needs to have an 85% reduction in greenhouse gas emissions. And now, obviously, an 85% reduction in emissions only gets you 85% of the way to net zero. And so that remaining 15% difference, the expectation is that we're going to have it sequestered by the lands and forests of New York State. And that's something that we've got a lot of good research that suggests that sort of natural climate solution is possible, but it requires active landscape management to promote carbon storage in your forests across the state. And to do that sort of active management, you have to be able to both measure how much carbon is being stored in forests right now, and you need to be able to monitor it over time so that you can actually track the success of your management activities and change course if you're not on track to hit your sequestration targets. And actually getting that data, actually measuring and monitoring that is really hard because New York State is huge. I mean, y'all from the Western states are going to laugh. It's the 27th largest state, but it's still a very big area if you're going to try and actually measure every single tree for how much carbon it's storing. The closest we get is the USDA's Forest Inventory and Analysis Program, or FIA, which has a set of 5,000 plots across New York State that they go out and actually measure the trees on to track how much carbon is being stored in forests. And the FIA is fantastic. I think it is flat out the best inventory program of any country in the world right now, but it has some limitations when you're trying to track this sort of sequestration. First off, these 5,000 plots are measured on a rolling 7-year interval, which means that if you're trying to, over a short time period, track how successful your management activities has been, this data set doesn't really get you there. And similarly, the FIA only measures forested areas. So if you're interested in things like abandoned agricultural land converting into forests, which is an extremely important source of carbon storage, the FIA can't track that for you. You can't use this data set to get there. And last but not least, each of these 5,000 plots is actually made up of the system of 4 plots, which gets a little complicated pretty quickly. But the point I'm trying to make is the relevant piece of these 5,000 plots is these 4 24-foot radius subplots that they go out and measure, which, because these plots are extremely small, 24 feet is not that big of a circle, you get a extremely variable measurement, which means that generally speaking, if you want stable estimates of how much carbon is being actually stored in a given area, you need to aggregate up all of the field measurements across usually a county or maybe even the entire state, which makes it really difficult to use the field data to actually plan your management activities and track how successful you've been, which is a problem when we're trying to do this sort of landscape management. So this is where my lab comes in. We've been applying machine learning techniques to remote sensing data to try and extend these field measurements to something that we can use for that sort of targeted intervention. And so we have this new preprint out, high-resolution landscape scale biomass mapping using a spatiotemporal patchwork of LiDAR coverages, which is goes into the technical details of what I'm going to be talking about a little more than I'm going to right now if you're interested. And again, it's linked from the slides, which are linked at the end of the presentation. But basically what we do is we take remote sensing data, so in this case, usually airborne LiDAR, and we associate it with those measurements that the FI is doing on the ground. So we have the field measurements of how much carbon is being stored, and we're able to calculate a lot of descriptive predictors that describe what the forest looks like when it's storing that much carbon. We can then take that data and run it through a modeling process, and we use a multi-tiered model process. I spoke about this at a recent ESIP meeting, so I'm not going to spend that much time on it now. But basically, we've got a random forest, a gradient boosting machine, and a support vector machine that we fit to the same set of predictors and generate predictions from. And then we take those predictions, fit a linear regression to them to combine them into a single ensemble model. And from that linear regression, we generate our single final prediction. And by going through this process, we're able to extend the field measurements that we have at these small individual locations across the state and instead generate predictions everywhere that we have LiDAR data, which these days it's everywhere that's colored on this map here. It's about 2/3 of New York State's entire footprint. And so by going through this process, by getting our field measurements, associating it with remote sensing data, going through the modeling process, generating predictions, we wind up with what is the most complete map of New York State's biomass at a relatively, it's a moderate resolution map, technically 30-meter pixels. And this map has already been extremely useful. We work really closely with the state of New York and with some partner nonprofits who are already using this information to prioritize their conservation activities. If you live in New York State, this map is helping dictate where your tax dollars go, which means that it's really important that we're generating an output that people can trust, that people have some amount of faith in, which is a challenge because as we've been finding, if you bring someone a map and said, I used AI to make this, you get met with a lot of skepticism. I really like this Scientific American article. I think it is extremely well written and really reflects what's become sort of the mainstream opinion of AI machine learning approaches in recent years. And the article is titled, "The Media's Coverage of AI is Bogus." And so to just steal 2 quotes from it real fast, the press will have you believe that machine learning can reliably predict whether you're gay, whether you'll develop psychosis, whether you'll have a heart attack, and whether you're a criminal, as well as other ambitious predictions such as when you'll die and whether your unpublished book will be a bestseller. It's all a lie. Here's how the lie works. Researchers report high accuracy, but then later reveal, buried within the details of a technical paper, that they were actually misusing the word accuracy to mean another measure of performance related to accuracy, but in actuality not nearly as impressive. I really like that quote because our experience has been that this is the mainstream opinion of AI and machine learning when you bring people outputs from these models. People do not inherently trust the outputs of AI systems. They're actually inherently skeptical of the results that you're presenting. And so if we are generating maps that are being used in ways that impact people's lives, it's really important for us to try and find ways that we can build back lost trust and try and build a base of confidence in the results that we are using, that we're presenting. So I'm going to talk a little bit about some of the approaches that we've been using to try and build back some of that lost trust as part of this carbon mapping project. If you're interested in some of the specifics and links to some of the methods, I had a blog on the ESIP website about a month ago that went into detail of some of these approaches. But I also want to make sure I'm taking a second to emphasize that I'm just describing the things that we have been trying so far as part of this carbon mapping project. I don't think that we have completely nailed this yet. We're still learning as we go. And so if this is something that you are interested in, that you think a lot about, my contact information is at the end of the slides. I'm on the ESIP Slack. Please get in touch with me. I would love to talk more about this. Anyway, so on to the ways that we are attempting to build that sort of trust. Well, one thing that we really emphasize with our group is that we only discuss the accuracy that matters, which is to say, we only discuss our accuracy in terms of on-the-ground measurements that weren't used to build the model. And so the first part of that we're using a holdout set when we're actually measuring our accuracy, feels extremely basic. That feels like a machine learning 101 concept, that you shouldn't be presenting your accuracy on the same data that was used to train your model. That resubstitution accuracy is an extremely optimistic measure of how well your model performs. And yet, in the applied literature, you still see resubstitution accuracy presented with the same weight as at a sample holdout set accuracy. And I think that that's part of the reason that we've seen really low levels of trust in these systems, is that a lot of people are not being properly careful when they're presenting accuracy numbers. A related one that we've run into is when we are comparing our model to other models of biomass, to other products that might be in use, we make a point of not reporting accuracy against these other products. We only report agreement between the models, because when you're dealing with the outputs from a machine learning model, this is what this graphic is actually representing. Machine learning models will always generate predictions with less variance than the data that was used to train them. So this graph, the gray points are the original data that a model was fit to, and the blue is its generated predictions. And so if you are testing your accuracy against the blue points here of a model that is theoretically actually modeling the gray, so in our situation, if we're comparing our accuracy to another biomass model rather than to actual measured values, you're giving yourself an artificially easy task to evaluate against. And so we make a point of only talking about comparisons between models in terms of agreement rather than accuracy, so that we're not misleading people about how well our model performs when they're actually on the ground with a map in their hand. A related concept here is that we make a point of breaking out our accuracy spatially, so that we represent areas where our model does better or worse. And so here, for instance, you can see there's an area in the southwest of New York, which our model is just much worse at modeling. And that's something that we understand why that's happening. It's a forest that is in the Allegheny National Forest. It doesn't look like most of the rest of New York State. It's much bigger trees. And so our model performs worse there. But if we're generating predictions in that area, we need to tell people that our model does not do as well in that area. We need to be properly representing our accuracy in a way that matters to these people, to our end users. Relatedly to that concept, we also make a point of aggregating our predictions to multiple scales and assessing our accuracy at those scales, because we're producing our predictions on a 30-meter resolution, but most people don't really care about our 30-meter pixels. They care about how much carbon is being stored on their property, in their town, in the county that they manage. And as a result, they're going to be aggregating these predictions to a different scale than what we're presenting them at. If we know that that is a use case for these models, it's important that we're talking about accuracy in terms that our end users care about. And so we make a point of aggregating our predictions both to the relevant administrative boundaries that we're expecting people are going to be using these at, but also to arbitrary polygons of different sizes, so that if someone takes our predictions and is trying to figure out how much carbon is being stored on their land trust property, they can look at results we already have to tell how much error there's going to be in that estimate. And then last but not least, something that we've been doing more and more of recently is working with applicability domains to determine where our model can and can't safely generate predictions. I'm not going to get deep into the math right now, but applicability domains is just a way of classifying if new observations are similar to things your model was trained with or are too far removed for you to generate good predictions. And so this is a map of our applicability scores across the state. Brighter is worse. And you can notice that in the middle of Manhattan, down in the south, in the high peaks up north, these are areas that our model does not do particularly well with. It wasn't trained on that data. And so if we're producing predictions there, we need to flag that our model is probably not well fit for that area. Similarly, we can also use this to identify areas that the data that's available isn't fantastic. That's why we have such harsh right angles in this map, is that it's areas where maybe the company that was collecting the LiDAR data changed pilots or changed the sensor they were using. We're still generating predictions in this area, but it's important for us to flag that these are areas of concern for us. So those are the approaches that we've been using so far to try and build more trust in the outputs of our models. We're looking at ways that we can do more of this, though. We're trying to identify other assessments that our end users will find useful as a way to understand the products that we're presenting them. At the same time, we're also trying to figure out how we can do this sort of thorough accuracy assessment and not really overwhelm people. We don't want to be giving them a several hundred-page data dictionary at the same time as the actual data product itself, because that's a way for them to just start ignoring our accuracy assessments. So we're trying to be comprehensive in how we present these assessments, but not flood people with too much information. We want to make it really tailored and really useful to our end users. So that's all I got. Thank you so much for your time today. This work was supported by the Climate and Applied Forest Research Institute at ESF. You can find me on everything at Mike Mahoney 218, and these slides are on my website at mm218.dev/ESIP 2022. Thanks.
Thank you, Mike. I agree with all the points you make about accuracy of the one question.
I wonder what you think. This is Renee Seaver. I wonder what you think about trying to punch upwards instead of punching downwards, and look to how we change the organizational culture, or say journal editors, so they're not always, because they're as drawn to sexy applications, regardless of the actual accuracy or pairwise comparison. So, you have any thoughts on how we change journal editors? I mean, this is like a long-standing problem with, hey, we confirm the null hypothesis. Oh, you can't publish off of that. So,
Yeah.
any thoughts on that?
Yeah, I'm of two minds on this one. So I do think this researcher in Germany, Hannah Meyer, has been doing excellent work recently. She's written a lot of papers on ways to assess these sorts of models that are getting a lot of traction. So she had one recently talking about global models of ecological variables are generally useless. They generally are using field data that's not a random or probability-based sample, and so their accuracy assessment doesn't reflect reality. And based on the traction that work has been having recently, I'm optimistic that this is starting to change. But as far as how do you get past the sort of hype culture that really drives a lot of this work, a lot of the large-scale AI machine learning projects, I think a lot of it just has to come from researchers and hopefully agencies demanding better accuracy assessments and demanding better understanding of the data that they're actually working with. I don't know how you do that systematically, but I've seen some corners where I think it's trending in the right direction.
Awesome. Thank you so much, Mike. Next speaker is going to be Doc. So he is already on the slide that you can see. So he made his presentation.
How do I find the data I need on EDC? Hello, my
How
name is
about now,
Todd Newman.
Mike?
I'll be giving a talk on machine learning and the Earth Data Cloud. I am part of NASA ESDIS, so let's begin. So, summary of this talk is what is NASA Earth Data Cloud? How do I discover cloud data on that platform? How do I access data on that platform? And we'll be talking about two ways to do that, either via HTTPS or AWS in-region S3 API. And then provide some examples of that. And so finally, some important things to know about Earth Data Cloud when accessing data. So as an ML practitioner, why do I care about NASA Earth Data Cloud? Well, you need data and you need lots of it. NASA Earth holds a lot of data. By the end of 2022, we will have 71 petabytes of data for you. Right now, around 47 petabytes of that is on the cloud, where you need it. And our strategy involves prioritizing our most popular data sets for early cloud migration. So how do I find the data I need on EDC? We provide a programmatic discovery API that allow you to find exactly the data you need efficiently using a two-step collection and file search paradigm with extensive filtering and formatting capabilities. We also provide a state-of-the-art user interface in the form of Earth Data Search, what can be used to filter your search by cloud data only, for example. The results of that can contain cloud-specific information such as region, buckets, prefixes, and credential information. We also provide a Stack API. This allows our users to access data using Stack-enabled tooling like Index Stack, etc. Stack is rapidly becoming the de facto catalog format for Earth Science in the cloud. So I know how to find the data I need. How do I access it? Step one is registration. You need to register with EDL and use those credentials to access data via HTTPS and/or AWS S3. EDL uses a straightforward user interface to register. Anyone can do it, and it's free. If you wish to access data using the S3 API, you need to use those EDL credentials in conjunction with a Data Archives S3 credentials endpoint. You can find this endpoint in the metadata of your data of interest. Step two, accessing the data through EDC. Now you have valid credentials, you can access your data. EDC provides two means of access, traditional HTTPS access and the cloud-native AWS S3 API. With S3, you can bring your compute to the data and unlock economies of scale in terms of both compute and scale of data accessed. Here's a Jupyter notebook demonstrating HTTPS access using Python from discovery to download. So the first step is using the CMR API to do a collection search using a filter, in this case, filtering it to a particular provider. This provider is PODAC. It's more specifically PODAC's Cloud Archive. This means that all of the data you get back will be cloud native. You could also use a filter that says, I only want AWS hosted data if you want a more broader scope than just PODAC, for example. Once you found a data set of interest by extracting its ID, you can then do a granule search for granules within that particular collection. You can add additional constraints to this, like spatial or temporal and numerous other filters that we support. Then once you found your granules of interest, you can interrogate that metadata to find the download URL, HTTPS, to actually download the data. And then finally, you can use the Python request API to do a get on that data. And you can see here that we've done that and outputted the size of the data that you've downloaded. And it's as simple as that. And you can see this link at the bottom of the display showing a public access point for the notebook I'm just describing here. Now, here's another Jupyter notebook demonstrating S3 access using Python from discovery to access. So we've done the same collection query here using PoCloud. But at this point, we're also going to extract some additional information about the collections we're interested in, namely where they are in AWS Cloud, i.e. which region, and an endpoint for obtaining AWS SDS credentials so that you can use the S3 API in conjunction with those SDS credentials to do things like copy data from buckets or list the contents of the bucket. So we do a request for the metadata associated with a certain collection, and within that information, we can extract the AWS region and SDS endpoint using the direct distribution information section of the metadata. Then once we've got that, we can use that collection to, again, as in HTTPS, do a granular search. This time when we interrogate the granular metadata, we'll be looking for a different type of link that describes the S3 URL. And from that, we can extract the S3 bucket and key. Once we've got that, we can move on to accessing the data. Step one of that is using that STS credentials endpoint in conjunction with our URS credentials to get our STS credentials. Then we can use the Boto3 Python library to interact with the S3 API using those extracted S3 endpoint credentials, i.e. the access key ID, the secret access key, and the session token. Note here I'm printing out the STS credentials expiration date. More on that later. So then you can use the get object API call on the S3 client, giving it the bucket and the key, and you can access that data. And we print out the amount of bytes you've got when you do that get object call. Again, this notebook is public and the URL to it is mentioned at the bottom of the slide. So that's how you do S3 access and HTTPS access on Earth Data Cloud. And I've given some demonstrations of how to do that in some trivial examples. There are some important things you need to know about access to data through NASA EOSTIS and Earth Data Cloud in particular. So, for EDL tokens and their interaction for HTTP access, they expire after 3 months. So after 3 months of using an EDL token, you will start getting errors saying that that token is no longer valid, and you'll need to get another token. And the instructions for doing that are in those in these slides and in the Jupyter notebooks that I mentioned earlier. Also, those EDL tokens are federated tokens in that they can be used for data access for any of our providers, whether it be PODAC, JPL, or JESDISC at Goddard Space Flight Center. So those are the important things to know about HTTPS access. For S3 access, there are a number of other things you need to know that are important. For example, all EDC data resides in AWS, specifically US West 2 region. AWS S3 API usage is limited to in-region access, i.e. you have to have your compute running in US West 2. If your compute is running off the cloud or in another AWS region like US East 1, you will not be able to use the AWS S3 API. The limitations on the S3 API usage, even when in region, are for limited to list and get object. So you can list the contents of a bucket and get any of the objects in that bucket using that API. AWS STS tokens expire after 1 hour. So each hour, you will need to refresh that token through the STS credentials endpoint. And finally, each provider or archive within Earth Data Cloud has its own tenant account. PODAC has one, JESDISC has one. So if you gain STS credential tokens from PODAC, they will work for PODAC for that 1 hour. But if you try and apply those same credentials to those same token values to data that resides in JESDISC, they won't work. You're going to need to get credentials from that specific endpoint at JESDISC, which is detailed in the metadata of all of JESDISC's cloud-based data holders. And that's it. Thank you very much for listening.
Thank you, Doc. If you want to sort of understand AI workflow, this is project very strict stuff. Because the one you get, you have to and then if you don't data, get your result and insights. examining and prepare simulations. If you want to automate your whole pipeline, that is okay, so you can send your questions through the notes or person. Our next speaker is Chen from and she is going to talk about cloud-based data backup service for quite popular. And we're going to think about how to use AI. I think it's really important because most of the time the AI practitioners is spent on the data collection. Match up is one constant. We have to match visions function. So training a model, that's kind of essential. Welcome.
So can you hear me? I've learned my lesson. Next time I'll bring high heels so that you can see me at ESEP. If I stand here. Okay. So thank you for inviting us. In full disclosure, I'm from JPL, but I have no experience whatsoever in AI and ML. But we did get invited to talk about our cloud-based data matchup service, which is CDMS. And so I'd like to use this opportunity to actually have the audience here. Thank you for sticking around on Friday in a cold room also, to give us some feedback on what you think are potential use cases for our service. So I'll describe what the goals of our service has been, and very interested in hearing from the cluster, from the community. Figure out how to use a Windows machine. So just an overview, which is that our CDMS, the original intention is to provide a capability that is generalized, that would, when a user gives a geospatial reference, a temporal reference, retrieve satellite observations, and then be matched or co-located in situ and satellite observations to the primary. And this, we've heard open science, open source. The software stack that enables this service is an Apache, part of the Apache Science Data Analytics platform. So it's an Apache Incubator project. We do plan, or we're looking towards graduation as a top-level Apache project within this year. It's also a collaboration. If you notice my title slide, it's not just JPL. It is a collaboration between JPL, Celdrone, NCAR, FSU. So we have I'm very fortunate to have be able to collaborate with many folks across different institutions. So why is CDMS needed? If you notice on this slide, there's no mention of AI ML, but that's why we're here. We wanted to add that to one of the potential use cases, but that's really used for our CalVal of satellite retrieval algorithms. So every time we have a new NASA mission, such as the upcoming SWAT, there is a time period where the science team has to co-locate data to calibrate, validate the instrument. There's also decision support, there's scientific investigations, quality control of the surface marine observations, and acquiring co-located SWOT data to provide ancillary variables to data sets. And this is an age-old problem, co-locating data. So, what we're trying to do is really eliminate the need for the community to have to create one-off matchup programs and downloading all the data that they need to co-locate onto their machine. So here is a sample use case from a published paper, 2019. Using Celdrone to validate satellite-derived sea surface salinity and sea surface temperature along the Baja coast. As you notice, we are partnering with Celdrone for our research. So that's a sample use case. Actually, back to this is, so what we're trying to do with our service is to be able to also, in our validation, replicate some of the findings from research papers that have used co-located data. Another sample use case is co-locating satellite observations to support studies on air-sea interactions. For example, to answer the question of, does higher SST influence wind speeds during regional ocean heat waves? This is the architecture for CDMS. You've heard a lot on federation, and the idea is that the in-situ nodes are spread across, wherever the data provider has the data. So there's NCAR, Saildrone, JPL, COAPS, and all the satellite data is hosted at, let's say, PODAC has the oceanography data, or LP with land data. And when we deploy a system like CDMS, the idea is that we can co-locate, have a service that would bring the data, the in-situ data from wherever it is into the centralized system where the satellite data is hosted and perform that co-location. I've also learned a new term this week at ESIP, which is ARCO, Analysis Ready, Cloud Optimized. I think that it changes year to year what we're calling it. But the idea is very similar. Satellite data, we're chunking it up, toweling it so that we can do enable, fast lookup and parallelization. So that's also the idea behind CDMS. We are leveraging the scalability of the cloud by tiling up the satellite data, and then the metadata for each tile is also indexed. This could be ZAR, this could be whatever the latest new ARCO format is, but the idea is very similar. So for the in-situ data, so that my previous slides covers the satellite data. For in-situ data, what we've done is, the problem with in-situ data is it's very heterogeneous. The metadata is all over the place. Field data, in-situ data, this has, I think, the same issues, bottlenecks. Our team is trying to simplify access to it by leveraging standards. And what we've done for specifically ocean in-situ data like ship, Saildrone, is develop a JSON standard where the source data could be in a MySQL database. It could be NetCDF files, but we're providing a way to translate it to a common JSON so that it can leverage this platform, the cloud, and ingest into standard Parquet files. So you've already heard Parquet in a lot of the talks this week as well. This is what the schema looks, snippets of this JSON schema that would describe the in-situ data or the translation. We're not making up more vocabularies. We're really reusing the vocabularies that are in existence from NERC, from that's out there. But so that is not, no, we're not reinventing anything. We're just really trying to adopt standards that are there already. This is the matchup algorithm inputs. So, what does a user need to provide to retrieve the co-located data? Now, there's obvious parameters, which is you need your primary data source. You need to specify what your secondary data source is, the temporal spatial region, and very important, what I really want to highlight is tolerances. So, we need to, a user needs to specify, what is the time tolerance? Is it a second that we would apart that we consider a match? Is it an hour? Is it, depending on the resolution of the primary and secondary data sources, that will vary. Similarly to radius tolerance, which is it 1 meter, 100 meters, 1,000 meter apart that you would consider 2 points a match. There's also, you can filter by platform, depth, science parameter, and whether do you want the API to return one-to-one match or one-to-many. So your primary could be matched to one or more potential matches. Do you want all the matches? So that's something that the API also provides. I'll describe really briefly what the parallelization and the matchup algorithm does, but the concept, this is, I consider it an application of like saying ARCO data, but you query the primary data store to retrieve all the satellite tiles that match your region of interest or AOI. And then for every single tile, the parallelization comes in by querying the secondary data store, and now this could be in situ or satellite data. And then we create a tree for fast, what we're calling KD trees, to do the fast match, and we construct the results. And the output format could be JSON, could be NetCF, could be CSV. And this is where actually I have a slide on standardized JSON output. And again, they're in the output, the NetCF output, reproducibility we understand is very important. So the parameters that were provided to the API is also an output in the header file so that it can be reproduced. This is a sample JSON matchup response. This block, you can see it's chlorophyll from a satellite level 4 data in the primary block, and then in the matches block, it will return what it considered as the closest match from a sail drone measurement in and its values. So what this is you've seen Jupyter Notebook's demo, you've seen a lot of talk about how, what it enables. And by providing an API access to retrieve matched data, a scientist, a user, anyone can really invoke this API, retrieve the results, and generate plots, do their studies however they want. In terms of near-term goals, what we're working on, we're funded for 3 years, and we've already, we have a year and a half to go. So we're looking at deploying this publicly and making it accessible in AWS for selected data sets. We can't onboard a lot of data, but we have identified data sets that we could use to validate the algorithm and validate some of the use cases that we've identified. So that's one of our near-term goals, and we would like to demonstrate this capability to potential adopters. Now, this could be NASA DAX. This is an access-funded project, so we do have pitches, discussions with DAX, but also the science community in general. So, an avenue like ECIP, talking to everyone here, we are exploring additional cloud optimized formats like ZAR. Can we, instead of using this NoSQL data store for our satellite tile, there are already, let's say the MER ZAR is in open and available in Amazon. Is that something that we could use for performing data matchup, data collocation? And two other things that we'd like to focus on in the near term is supporting large matchup requests. So, think global scale. Right now, we could get a collocated like Gulf of Mexico region, but we also want to support, longer time span, larger region. And then also extending existing visualization interface so that a user can go to the web and explore what potential data they want to collocate. So this is where my question for everyone here comes into play, which is what, I'm very much interested, and you can find me on the ECIP Slack as well, on what are some of the known AI ML use cases that you have that have a need for collocated data. I have an example that another PI was funded for access as well. And they also had to develop a one-off, implement a collocated algorithm for satellite to satellite. It's very specific for cloud property retrieval. So I'm no expert in what you see here. Jian Wu, the PI of the Access project, actually provided these slides, the materials that you see. And I think my understanding is that there's two types of sensors, active and passive. Active is more accurate, but the passive sensor has more coverage. So what they have done is they need to find overlap or collocated data between the active and passive sensor so that they can train the model and use that to predict in the measurements collected by the passive sensor that has a wider coverage to see if they can use that to predict cloud properties in the passive sensor measurement. I think that was it. So thank you everyone for listening to my talk on a very cold Friday. Questions?
Yeah, this is going to unlock the artifacts. So the question is, if I understand right,
Correct. Yeah, that's something that one of our project was actually funded. I want to say 2015. A while ago, and initially we only started with satellite to in situ, but we've had since expanded it to satellite because we know there are use cases.
Yeah, actually, I have a question. Is this like matchup algorithm can be binary other like high cover? Because we have like a slow cover machine learning workflow, and one of my major tasks is to match the segment data with the slow tail station, and some of those like pixels, they can only use the functions from many away.
Yeah.
So can we use this matchup service to give like a ranking of how we should, whether use it or whether coming as a match or just discard it? So,
Right. So I think our focus is generalized. So the tolerances are all configurable. You can use 5 meters, 20 kilometers. You can vary that. We haven't expanded outside of the oceanography data sets yet because funding doesn't allow us to do everything. But there's nothing in our software stack or the matchup algorithm that would exclude other domains. So I think because our team is very experienced in the oceanography data, we're really using this to validate the system that we're building. But we have talked to other folks like at LPDAC land that has land data, so there's potential, I think, for that.
nice.
Thank you.
Thank you so much. Right. Last. Thank you. Okay, so this is the last presentation, and I believe everyone would like to see me. And I believe you already heard about the GeoWeaver, and which is the homegrown. Oh, sorry. Yeah, the homegrown software within ESIP. So I'm super excited to introduce this
tool because we already worked on this tool for 4 years, and we believe we're almost there to be a stable software, and it's exciting. So I'm gonna talk about the purpose is like increase our productivity and the reusability of AI, which you have if you already worked on ML, you will know that this is super like very difficult. It's like higher barrier for everybody to get over with. So many papers already address that AI has a serious problem on reusability and reproducibility. And actually, it's because the randomness in the AI. Because every time you run the AI model, you will get something different. But it's necessary to introduce that randomness into AI because the world is changing, and the change is kind of like a random, but it has a trend, but it's not like determinist, you know. So it's like every time you run the model, you will get different. That's reasonable because the world is behaving like this. You will never predict the tomorrow very accurately. Like that's kind of like determined by the physics. So every run of the AI model is a different run, and what you got from the AI is kind of like the fix, the history. And if you want to use that history to predict the future, that's gonna be a question about like philosophy or something like. So we are not mentioning AI is like replicable because it's non-replicable. You cannot regenerate exact same model in 2 runs. So that's the randomness of the AI. It's kind of like embedded in there. So it's a little bit different from the existing models we are using, like a numerical model or whatever model that fixed. The rules is fixed. Every time you run it, you get the exact same results. It's not the situation AI practitioner is facing. So I think that's the main problem. The AI specialist has super low productivity because every time you run it, it got something different. Then you kind of like lost. The experiment is endless because you never know the next round is. So how do I validate my results if it changes all the time? It's like you are observing the atoms or some like physics phenomenon, and it changes every time. It's really hard. It's like uncertain all the time. So we need an observer of AI. Because of the randomness, we never know whether AI model predicts the event correctly without going through that event. So just wait till the event happens. So it's kind of like a Schrodinger's cat. So before you open the box, you never know. Even the model is changing. Even if you do not use the model to predict the results, you will never know whether it's correct or not. And it could be both. So that's why AI practitioners, especially the Earth AI practitioners, because we're facing the real world. We are studying the real world, and we are kind of stuck, like using AI and do something. We got a very high accuracy that is based on historical data, and we never know how it will, perform in the future. So observing AI is very important. It's like you have to have this observer to determine that which universe you are in. So AI workflow observation and recording must be conducted for every run. Not only for the best run, you think that it's best, which is not, because you never know which one is better. So we have to record everything. That's kind of like if you want to improve your productivity in AI research, you have to record everything. This is an example that we have done with snow cover mapping, but we also have the same problem in other AI research, like the SWE, slow water equipment forecasting, and air quality modeling, CMAC. All our use cases facing the same problem. Every run is different. And the first run give you a model, and model predict these days correctly. next round give it another model that is predicting that day is wrong, but we didn't change any of the source code. That's the problem. So it's kind of like mysterious. If we want to deploy this model into the production, we're gonna use the first round model because we tested. But whether the second model will outperform the first model in the future, we don't know. It's kind of like it's really hard to control that part because the future is uncertain. And let's go back to GeoWeaver. GeoWeaver is designed for this purpose, record everything. So this is like the two history recorded by GeoWeaver. The left is the wrong one, the first round, the right is second round. You can see that the source code is completely the same, and the result is different. So MNE, as Mike said, is a accuracy matrix of the AI, which is totally unreliable. And but MNE, average error, MSE, the square error, I2 score, IMSE, every AI researcher is using them to measure the AI performances. And you can see the left and the right is slightly different. It's actually the square error is actually not slight. It's like left one gives you 49, the right one is give you 47. But this is totally the same source code produce two different models that has different accuracy. So that's why the accuracy reported by the AI research papers is totally unreliable. I totally agree with that. Okay, so the low productivity problem, how do we solve that at this stage? Because we have no control over that randomness. So how do we within our power, within the scope, to develop the software to help us to address that problem, at least at some extent. It's really difficult to deploy something that we don't have control over to the public. So that's why you see very little AI research result public to deploy to the public in earth science. I know that there is other things going on in the computer science industry, but right now I didn't see. At least we are still at the early stage. And one of the problems is without a full stack means not only the AI training, testing, validation, that is AI. All the pre-processing step, like from end to end, from the original data stored by the NASA NOVA in the AWS, starting from retrieving the data from there and feeding them, reformatting, pre-processing them into AI-ready format, and feeding the AI-ready data into the AI models and get the results. All these steps should be, packed, like it's wrapped into a full stack workflow, and that workflow is counted as a reusable and it's traceable workflows, and it's easier for people to understand what's going on there. So without this kind of full stack workflow, it's really hard to reproduce because all you get is a model, and then the model changes every time. So that's a problem, and the knowledge cannot be easily shared. And also, to make that work, we have to record the history. So AI model is really difficult to be trusted, and that's very true. Without the history, you will never know why you got this model and why it produced this result at this time. Okay, besides the low productivity, the knowledge sharing is a disaster. So if you have an AI specialist on your team and he or she wants to share her knowledge to you, it's really hard. It's like how to make it simple to transition his workflow to your laptop, and how to make it effortless to understand his AI full stack workflow, and how to make it easier to check let's say this students graduate from your team, and another students want to take over. So how to check your predecessors for AI realm history? Because without that history, it's really hard to understand and to see all those problems. You probably will spend the same amount of time repeating the mistakes that has already been go through and maybe fixed by the previous person. So it's really hard to share knowledge regarding AI research. So we developed this tool, GeoWeaver. So it's an easy productivity tool for any level of as data scientists to organize their source code of the full stack AI workflow and record all the model run history. So you don't have to actually click any button or something like that. It will do them under the hood. So because I'm an AI practitioner, I hope I have this kind of tool. So we designed it to be very usable and user-friendly for people like me. Yeah, this is it's an architecture. I think it's considered as a go-to software for anyone building AI workflows in a distributed environment. So if you have as a Ryan said, all you have is a laptop, lab server, institution computing cluster, and HPC somewhere. You can use them all in GeoWeaver. It's like you can store everything, source code history on your laptop, but you are using all this infrastructure in one place. It's like a one-stop solution. It can be deployed on some public server, so everybody can use the same instance, but I don't recommend it because of the privacy. Okay, so the user profiles, and I think many people can be users of the GeoWeaver. It's like especially a system administrator, like your lab servers administration, research scientists, obviously. If you are using Python shell scripting, you should use it because every time you run the script, it will be recorded, and you will appreciate that. I have been going through this kind of scripting for many years, and this time I have all the history. So that's amazing. It's like I will never forget because I will forget very easily. It's like I cannot remember what I have done yesterday. So yeah, I really appreciate this feature. Record every history of my script run. Okay, so the students will definitely appreciate the GeoWeaver because GeoWeaver will export the previous person's full stack workflow into a zip file, and they will receive this zip file. Everything is packed, so they import it into GeoWeaver. They will see everything. It's like one click, you will get all the previous person's the whole thing, like whole package. So students it will be easy for students to get it, import it, display it, and understand it. It's a graph, so it's not like a long, 7-page long Jupyter notebook or something like that. It's a graph, so you can clearly see what steps it goes through in that workflow. Engineering, of course, if you want to deploy the AI into some production environment, GeoWeaver will help you do that. Like cron job, run it every morning or every hour. You can just call that command line, use the GeoWeaver command line, run that workflow at the time you specify. And it will run and automatically pull the data set as an input and produce the predictions regularly. It's like, yeah, we use a cron job a lot. So all the numerical models is running on that, and as we can reproduce the something similar. What knowledge is needed to use the GeoWeaver? For the workflow creators, knowledge of the scripting, so Python shell. Right now we are supporting that, but we are thinking about supporting R, but it's not available yet. So we are focusing on Python shell. The data collection and AI engineering, of course, if you are AI practitioner, you have to know something about it. But if you just want to get that workflow and see what's going on there, you can just get the zip file and set up the GeoWeaver, which is very, very simple. It's just one command. You will get GeoWeaver on your laptop. Just go through there, go in there and check all the source code and output and models. The users, like the students or the colleagues who got your zip file, they will be able to read it if they have knowledge of the Python shell scripting, data collection, AI engineering. Okay, so this is the interface. I think I can display something here. If I have time. Oops. I don't know if I have time. So this is actually GeoWeaver. As you can see, this is my sweep forecasting workflow, and this is my training validation process. If I go there, I can see all the history I did and my students did. So anybody get the workflow, they will see everything, like all the histories you have here. And if you click on the view changes, you can see that the current model run and the previous model run. So you can see that I didn't change any of the source code, but the result is different. It's like average error, and it's a 4.04, and this previous run it gives a little bit worse performance in like 4.11. So you have everything. You have every run's input and output. Yeah, that's it. And if you want to export everything, like this entire workflow, you can just click this button and it will download all the source code and all the process history. And once it's downloaded, it's going to be a zip file, and use that zip file another person, the second person can just open that in the, using this button and import it, and they will have all your source code and all your history. And I think that's it. So, question? Okay, yeah.
I think this is really interesting. I'm just wondering how much you have tested it to see whether the models are reproducible when they put in the information in the workflow.
We tested a lot. Like I can do this all day. It's like run the model. Every time I got something different, but it has a scope. It's like it's not that different. It's just a slightly different. So once we experimented over and over, and we found that actually this accuracy is always falling in a scope that is tolerable. It's like in the production environment tolerable. Then we consider that it's the time to deploy it. Yeah, I can run it right now.
So what do you see this is how different this is with other ops, like tools that is already, for example, Azure.
You mean Angel?
Microsoft.
Oh, man, yeah. Well, this doesn't conflict with them. It actually can use the planetary computer and the Google engine. For example, this process is retrieving data from Google engine. So it's using its Python API, and it's as one step of the workflow. So
yeah, they also have their experience already. So how different work with their existing technology?
Well, I think there is many differences, but what came on top of my head is the history feature. Is that you have everything recorded, and this history is exportable, and it's actually in a plain JSON file. So even you do not use the GeoWeaver in the future, you can still read them on GitHub. If you put it in the GitHub, you can still read them, have access to all these histories. And maybe in like 7 months, people feel like, okay, so you already did this, and this is super helpful. That will mean something for the AI. It's like the knowledge sharing is much easier with GeoWeaver than if you are using the SageMaker. SageMaker is like everything is packed inside, it's kind of like under the hood. So it's not quite easy to access those things right now. That's my current thing.
Yeah, another area that yeah, it's an outward. So can you look at some
I didn't catch that question part.
yeah, whether model has they can generate to have some type of then yeah.
Well, actually, the model the model training is what I was talking about. If you are using the model to predict, then you can use the model. Every model, like every model run can use it to predict. But it's like a parallel universe. Every time you train the model, you get a different model, and the model will have a whole different set of the result. So it's like a snowfall or rainfall forecasting. You will have different data products from every model. All right, I think we're here. Thank you so much to stick with us on Friday, and hope we can see you in some of our ML monthly meeting. And we are working again. We are working on the practical AI. So all of this is really critical to make AI practical. So we are working on the practical AI white paper, and welcome everyone to join us there. So thank you so much.